Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. This is guided notes number 6 in the series on section 2.1, Composition of Functions. The idea of a composition of functions is that we can take one function and plug it into another one. This is often written in this way, but I prefer the following notation. They mean the same thing, and this really lets you know that it's g of x that's being plugged in to the argument of f of x. Whatever the output is when you plug x into g, you plug that into f and evaluate. For example, here we have a composition where they have put the function x plus 5 into f, who is itself the function 4x squared minus 4x plus 2. So what we want to do is replace every x that we see with an x plus 5. It's helpful to keep the parentheses so that we can see, for example, that we need to square the entire term x plus 5 here. Now we distribute and collect like terms. Nothing else is really required for this problem. Now, in general, this is in fact not true. It is not common, not generically true, that these two would be equal to one another. If I plug g into f, it's often different than if I plug f into g. Let's actually demonstrate that with the above example. Here we could have considered g of x to be x plus 5. And what we've just evaluated then is f of g of x. What about the other way? What about g of f of x? Well, in that case, I'm plugging in 4x squared minus 4x plus 2 into g of x. And g of x says take whatever you plugged in and add 5 to it. So this is just 4x squared minus 4x plus 2 plus 5, which is 4x squared minus 4x plus 7. And although we do have a 4x squared here, the other two terms are not the same, and so we can see firsthand that this is in fact a false statement. I'd like to show you two ways you can think about composition where we're plugging in a value. One is that we might want to get what is f o g of x itself as a function in terms of x, and then we can plug in 0. And so if I plug in the rules for g of x, 4x plus 7, into the rules for f of x, which says take 1 over that thing and minus 5 from it, we can see that we get 1 over 4x plus 2. Now, if I plug 0 into that thing, that would be the same as 1 over 4 times 0 plus 2, which is going to give me 1 over 2. Another way that we could proceed, though, is to take and simply say that this is g of f of 0. Now, f of 0 is going to be 1 over 0 minus 5, or minus 1 over 5 if we simplify that. Now, plugging this into g, we have 4 times minus 1/5 plus 7, which evaluates to minus 4 over 5 plus 35 over 5, which is 31/5. Similarly, for number 4, if I wanted f of g of x, I could take that as f of g of x, which means plugging in g's rules, or x squared minus 5x plus 6, into f's rules, which says take a thing and multiply it by 6. So instead, I'm going to multiply x squared minus 5x plus 6 by 6, and then I'm going to subtract 6 from that. Distributing and collecting like terms, I get 6x squared minus 30x plus 30. Likewise, if I reverse the order of my composition and we plug f of x into g of x, I'll need to take and evaluate in the rules of g of x 6x minus 6, which is what f of x is. This is going to give me the square of that, which is 6x minus 6 squared, minus 5 times that, which is 6x minus 6 again, and plus 6. To figure out what this is, we're going to need to first FOIL, and expanding this by our perfect squares rules is going to give me 36x squared minus 72x plus 36 minus 30x plus 30 plus 6. And combining like terms, we get 36x squared minus 102x plus 60. Now, as far as your homework's concerned, I'm pretty sure if you just plugged in this answer here, it would be fine. That would cut down on errors made in simplification. But you should also know how to expand a perfect square, how to distribute, how to collect like terms, and simplify. All right, let's figure this next one out. We want to take and plug into f what happens when I plug 0 into g. Well, if I plug 0 into g, that would be 8 minus 0 squared, but that's just f of 8. Now, f says take the thing that is your argument, which is now in this case an 8, multiply it by 8, and minus 2 from that. and 64 minus 2 is 62. Here, we want to take and plug into g. What happens if we plug 0 into f? This would be 8 times 0 minus 2. In other words, what is g of minus 2? Now g says I want you to take 8 and subtract the square of what you're plugging in. So we plug in a minus 2 here, and we get 8 minus 4, which is 4. Here we're asked to evaluate a couple expressions given a couple of graphs of the functions. Now remember, a graph tells me what the input and output of my function is without an algebraic rule. But for example, if I plugged in 3 into f, I would get 3 as an output. So let's just follow along with what happens if we plug various values into these graphs. We want to evaluate from the inside to the outside of these parentheses. And for example, if I plug in 0 into g, I should get 3. So this is f of 3. And we just saw that f of 3 is itself 3. Likewise, if I plug in 5 into f of x, so starting here, I get 2. And then plugging in 2 into g of x, I get 1. Here we have f of 1. This just asks us to plug in a value into f, which we can. Plugging in 1, we get 5. So this would be a 5 that now I need to plug into f again. And doing so, we get 2. So f of 1 is 2. What about g of 4? Well, g of 4 is 2. So g of 4 is g of 2. And then g of 2 is 1, which gives us 1 as an output in total for g of 4. Now the same maneuver can be done that we just did with this graph by using a table, which also tells us the values given certain inputs. If I look at g of 4, I need to use my x input of 4 to get 2. And so f of g of 4 is f of 2. Now what's f of 2? We go to 2 and look at f. That gives me 0. What is g of f of 7? That's g of f of 7. So we go to 7 and find out what f says to do. It says, I'll give you 5. Okay, so what's g of 5? We go to 5 and look what g says to do. It says that's 7. Very good. So really there's no problem. You're just following along what each individual piece says to do and then going back to your x column and saying that's my new input and plugging that into the function. So let's do that for f of 9. That's f of whatever we get when we plug in 9 into f. We get 2. So this is f of 2. And f of 2, we saw, was 0. So this is 0. Then we have g of 6. But what's g of 6? 6, g would give me back a 4. So this is really g of 4. Now g of 4, we go to our 4. What does g say? It says 2. So this gives us a 2 overall. Here we're asked to see a function as a composition. We want to know what two things are going on here. Well, we can see that there's an x plus 4, and we are taking 1 over that. We want to recognize those two parts. And they even say to us, hey, let one of your functions be x plus 4. What's the function you could compose with that in order to get our original function h? And the idea is that the other thing going on in h is this reciprocal pattern, which is what I want f to do. I want f to take in x plus 4 and give me its reciprocal. So if it's taking in anything, it should give me back the reciprocal of that thing. And then indeed, f of g of x would be f of x plus 4, which would be 1 over x plus 4, which is precisely what h was defined to be. Here's another one of the same kind. We're asked to see what's going on with x plus 2 to the 5th. Well, there's two things going on. Number one, we're adding 2. And then after that, we are raising this to the 5th power. And they say, all right, let f handle raising the thing to the 5th power. What should g do so that when we compose the two of them, we get this full h function over here? And of course, the answer is let g be x plus 2. Because then if I take f of g of x, this is f of x plus 2, where f is raising something to the 5th power, which is what we defined h of x to be. Now here we're asked a very interesting question, which is about the domain of f of g. What we could do first is figure out what f of g is. F of g is f with g plugged in. And if I plug in g, which is 7x minus 6, into f, which says take 5 times whatever that thing is, and add 2 to it, once we get done simplifying, we can see that we still have a line. So because this is a line, there's really no obstacles towards substituting in any x value you like here. If I can substitute in any x value I like, if I have no other reason to say otherwise, then the domain is all real numbers. When we talk about domain in the context of composition of functions, what we want to do is make sure that the input into a function is going to be within its domain. So for g, x needs to be inside of g's domain. This is also true in turn for the domain of f of g, because to get things started, we need to plug things in to g. So it has to work for g before it can work for f of g. But furthermore, the input into f is now the entire function g of x, or we could think of this as the output of plugging in x into g. So in other words, whatever is going to go into g, it has to be true that g of x is going to be in the domain of f. So we also require that x be in the following set. It has to be an element such that when you plug it into g, you get something in the domain of f. Here's an example. Let's say f of x is the function 1 over x. And let's say g of x is the polynomial x squared minus 1. Then f o g of x is going to be 1 over x squared minus 1. And what we can see is that, first of all, the domain of g of x is, well, the whole real numbers. This is a polynomial, and so it's not going to have any domain restrictions. On the other hand, it's no longer 0 that causes a problem, as it was for f of x. It's now the zeros of g of x. It's the output of 0 from g of x that causes the problem. We have to ask this question: when is g of x 0? And that would be when x is equal to plus or minus 1. And so what is the domain of f o g of x? It's going to be all of the points except 1 and minus 1. We have to leave those out. Here we have another example where g of x is going to be a function defined on the entire real number line. And f of x has the restriction that its argument, 6 minus x, is going to need to be non-negative, which could be written this way. Now let's see how these two things combine. I'll put that out to the side here. F o g of x is going to be 6 minus, and now instead of x, we have x squared minus x. And so notice that now, instead of having a domain restriction concerning the 6 minus x term here, we have one concerning this whole polynomial. So we really want to know, for our domain of the composition, where is that positive? So let's solve that inequality. Let's multiply by minus 1 here to make this easier to factor, keeping in mind that we must flip our inequality. And we have then factors of x minus 3 and x plus 2. And so we might solve this with the following diagram. Let's plug in a test point of 0. And plugging in a test point of 0, I get a minus here and a plus in these two spots. Now, we were interested in where this could possibly be negative, and that's going to be between minus 2 and 3. It's inclusive inequality, so we include our endpoints, and we have the following interval for our domain as such. For this next one, we actually have something where g of x, the internal function, has a domain restriction. We notice that the domain of g of x is going to be precisely the x's such that x minus 2 is not equal to 0. And so when we compose our two functions, we are going to need to also maintain this domain restriction. Let's consider the function f of g of x explicitly here. That would be plugging into f, the function g of x, which is 12 over x minus 2. And we then plug that into 1 over x plus 4, but now my x is being played by x 12 divided by x minus 2. And we see we actually have a compound fraction. So the great rule to keep in mind is that 0 must not be in any denominator, not in this overall second denominator with 1 over this compound fraction thing. This denominator here cannot be 0, and neither can this denominator here be 0. So we really do have these two domain requirements. We require that x minus 2 is not 0, and also that 12 over x minus 2 plus 4 is not 0. It's, of course, when x is equal to positive 2. And when is this equal to 0? When is 12 over x minus 2 plus 4 equal to 0? Well, let's bring my 4 over to the other side. Let's multiply on both sides by x minus 2, distribute, regroup, and divide off the coefficient. So we found that there are two forbidden values. This would be problematic. This denominator here would be problematic if x was 2. And this overall denominator in the compound fraction would be problematic if x was equal to -1. So these both must be forbidden values. We mustn't let x be equal to either 2 or -1, which as an interval would look like this. Let's also go and simplify FOG. The way we would do this as a compound fraction is to combine the denominators using the rules of fractions. And in order to get like bases, I'm going to need to multiply by x minus 2 on the top and bottom. Distributing the 4 and grouping like terms, I'll have a -8 here, which gives me 4x plus 4 over x minus 2. But then we're going to want to divide by this denominator, which means flipping and multiplying. So 1 over this fraction is going to be x minus 2 over 4x plus 4. And here, of course, we can see that 4x plus 4 shouldn't be equal to 0. This is how we would get, that x can't be equal to -1 again. But notice that we seem to have lost the domain restriction of x cannot be equal to +2. If we just looked at this, if we made the mistake of thinking that this was the function in its entirety, like without any history, well then, yeah, x is equal to +2 is an okay value to plug in here. It looks just fine. But that completely ignores what we had to do to get here. X was not allowed to be 2 in order to complete this move, or else this really is an undefined term here. So we always had x not being equal to +2 sort of baked into this cake. That's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.